In this presentation, we are going to be proving the fundamental theorem of conservative vector fields with Green's and Stokes' theorems. Firstly, let's establish some important differences and similarities between Green's and Stokes. So both theorems evaluate the circulation over the boundary of a domain, but the difference is that Green's evaluates it over the boundary of a domain that strictly lies in the plane, and Stokes extends Green's by generalizing that domain to be any surface in R3. Before we get into the proofs, let's recall the fundamental theorem of conservative vector fields. For the purpose of this presentation, we are going to be focusing on part 2, which states that the circulation of a conservative vector field over any curve will always be 0.
Now, let's prove the fundamental theorem of conservative vector fields for closed curves using Green's theorem. For a two-dimensional conservative vector field, we know that the cross partial derivatives will equal one another. Rearranging this, we get that the difference of cross partials equals 0. This difference shows up as the integrand in the right-hand side of Green's theorem, and when we substitute 0 for it, we can see that the entire integral evaluates to 0, showing that the line integral for a 2D conservative field around a closed loop is also equal to 0.
For a three-dimensional vector field, we apply Stokes' theorem, which states that the line integral of the vector field over the boundary of the surface is the integral of the curl of the vector field over that surface. However, we know for a conservative vector field that the curl of f is 0. Thus, as long as the surface has definite bounds, the right-hand side of Stokes' theorem evaluates to 0. Hence, the circulation of a conservative vector field around a closed surface, or around a closed curve in R3 is 0.
With this, we can conclude that in both R2 and R3, the circulation of a conservative vector field will always be 0. And this can even be generalized to further dimensions as well, so R4, R5. No matter what, so long as the vector field is conservative, the circulation will always be 0.